before we start a new topic, there's an interesting exercise, which is you take the Hopf bundle, which was a bundle over S2, and check that there are no sections. Which means that there's no smooth map from S2 back into E, such that it projects back into identity.
That's like related to like vanishing of sections, right?
Yeah.
It's like you get the chart number that tells you how many times a section vanished.
In the associated vector bundles, but not, I mean, just here that's meaningless. Yeah. So because we have an explicit trivialization formula for the explicit trivialization of this, you can just, you take any smooth map on the sphere into, like on one hemisphere of the sphere into E, whatever, in the trivialization, whatever you think can be. Then you apply the transition function to that, and you ask, can the result be extended into the second hemisphere continuously? And the answer is no, basically, because it's a thing that winds once around the circle. There's no way to like continuously extend it to to one of the poles of the sphere. Like the winding number will prevent continuity. But it's useful to think about that because usually in books people introduce vector bundles first, and then principal bundles or more general fiber bundles. And the intuition that you learn from vector bundles is very wrong when you try to apply it here. For instance, vector bundles always have sections, and that kind of screws with your picture of what a bundle looks like.
Can you relate these kinds of arguments to stuff like a Harry Potter, where you normalize the vector bundle, and you normalize the section of the vector bundle to get like a section of the sphere bundle?
Harry Potter is not about sphere bundles; it's about the tangent bundles.
Yeah, but you can't normalize if you have a non-vanishing vector bundle or
Yeah.
vector section, then you can normalize it and get a section.
Yeah, it's related. Yeah. The Chern number of the tangent level of the sphere is 2, and that's exactly the statement that every vector field on the sphere has to have at least 2 zeros. Anyway, vector bundles. What's the idea? So we want the fibers of our bundle to have a vector space structure. And so there's 2 ways to define that. First, you say it's a fiber bundle whose fiber is diffeomorphic to Rn, or some vector space, and each fiber also has a vector space structure on it. So within each fiber, you are able to multiply by scalars and add points. Okay. But what else should you require then?
So it's a fiber bundle, but the fibers are diffeomorphic to Rn. You have a vector space structure. So what more do you need on top of that?
Yeah.
So the fact that it's a fiber bundle automatically means the vector spaces are glued together, but you need their algebraic structure to work.
So we want some smoothness as usual, right? So the fibers have a vector space structure, but that structure has to depend on the fiber smoothly in some sense, right? And we need to explain what that means.
You glue them together using a convertible. You have the transition function,
Right.
So it's probably smooth map to GLN or something.
Or so you can, if you have a manifold dimension
Mhm.
and some vector bundle over it, then your trivializations can just be essentially hashes Rn times that vector space with sort of the simple vector space structure of just like Rm plus n.
Okay.
Where and then your transition function space should be
Is that right? So
But they should be not just smooth, right? The transition.
Your transition functions should preserve
Yeah, they need to preserve the vector structure. So that's exactly the statement that the vector structure depends smoothly on the fiber. Is that transition functions preserve the vector structure, which is equivalent to saying that they are linear, right, on the fibers. Which is why I will approach this definition from the opposite side, more or less. So let's see. Vector bundle, I will just write VB, is a fiber bundle whose typical fiber, fiber F, has a vector space structure and the transition functions are linear in the fibers. So that means that these transition functions tau alpha beta, they map from u alpha beta into the group of invertible matrices on F. Okay. And the rank of bundle is defined as the dimension of the fiber. That defines the rank. Okay. So now I need to explain why that is sort of the same as what we just discussed. First of all, there's a little ambiguity here because this seems to depend on the choice of the trivialization, right? How do I deal with that? Because like if I trivialize one way, they will take values in GL. If I trivialize another way, they will take values in GL conjugated by some diffeomorphism, which is not GL. Right? Hmm? See,
there exists a bundle atlas with that structure.
right. I mean, that's basically what I'm saying. But the question is, why is that okay?
I mean, if the statement is there exists a bundle atlas, then that's not an apples to kind of statement about the bundle, right?
Right. Okay, sure. But the other thing was so previously we said that the vector bundle is a bundle whose fibers have a vector space structure. That's not what I'm saying here, right? I'm saying here that the typical fiber has a vector space structure. That's not the same as every fiber having a vector space structure. Okay. So we need to prove basically a proposition, which is every fiber of a vector bundle, E over M, is naturally vector space itself. Right. So up to basically global bundle isomorphism. So bundle.
wait, why is that not part of the definition?
because I never said that each fiber is a vector space, right? I said the typical fiber is a vector space.
But the diffeomorphism in general could destroy the vector space structure.
No, that's the thing. There is no vector space structure on the fibers, right?
Or not destroy the
So,
bond.
right. So we have the so pick any.
The definition of fiber only applies to fiber at a point. Diffeomorphic to a different fiber. It doesn't mean that the vector space structure of the different fiber would necessarily be diffused onto the fiber at a point.
So we have these trivialization maps, right? The bundle atlas going from the restriction of the bundle to the direct product. Now this is a vector space, right? This map, chi alpha, is nothing but a smooth map, right? There's no other restrictions on it. But now using this map, we can induce a vector space structure on the fibers of E, right?
Are you saying whose typical fiber? So typical fiber, that's like your model fiber. It's like some abstract fiber sitting somewhere. It's only
To which it's diffeomorphic.
So you're not saying that pi inverse of a point always has a vector space structure for all points. So that's what you're proving.
Yeah.
Okay.
Induce vector space. Let's induce vector space structure on E sub P, right? The fiber above P, via these chi alpha, assuming that P is in U alpha. Okay. What does that mean? Well, that means that if I have two E and E prime are both in EP, then how am I going to define E plus E prime, let's say? Right, so I want to say it's chi alpha inverse of P comma, it's not pretty, projection number 2, chi alpha of E plus projection 2, chi alpha E prime, right? So just add them in F. Okay. So the main question here is then what, right? What's the potential problem with this definition?
Is it still like the same
What do you mean by that?
Like, does it have all the properties we require addition to have on vector space?
I mean, definitely does. There's a plus sign here. That's not the problem. The problem is this alpha, right? We need to check that this doesn't, right? If this E belongs to multiple U alphas, restrictions to multiple U alphas, then they all need to give the same definition of E plus E prime. So if P also belongs to U beta, so the intersection of U beta and alpha, then we need to check, this is sort of the definition in alpha. We need to check that this definition gives the same as this definition. How do we check that? Right. So.
But then couldn't you just say, without going through this argument, that okay, since the dimension is the same, then the vector space structures are isomorphic? In both the classification.
No, that's not the same. Isomorphic is not the same as the addition being equal in different, right? It's one thing to be able to add on the typical fiber, which is what I'm doing here. It's another thing to be able to non-ambiguously add on the bundle itself, right? So we need to show that. Well, let's take E plus E prime and write this. It's equal to that, right? And now I want to re-express, I want to insert some chi betas and chi beta inverses in there, replace them with taus. Okay, So I will write that as what's F? Oh, okay. Let me, yeah, this should simplify the notation a little. Yeah, let's write F alpha for chi alpha restricted to this fiber. Okay, so that I don't have to write that stuff all the time. Oh, and then I guess projection too in there. So this will be a map from the fiber into F. Right, that's it. We'll just deal with those on one fiber. And then this definition just becomes E plus E prime equals F alpha inverse of F alpha of E plus F alpha n, right? But now we can rewrite this as right, because this thing is equal to F alpha. Then tau alpha beta F beta E1 plus tau alpha beta F beta E2. Oh, E and E. Okay. Right. So I just basically I just use the fact that F alpha equals tau beta alpha F beta, right? F alpha, F, sorry, F beta, is that right? Okay. But now we notice that these are all linear maps, right? So this cancels with this. So we get which is our definition in the beta chart. And of course, the same with scalar multiplication. So that's basically it. So we can pick any atlas whose transition functions are JL valued, and from it induce a vector space structure on each fiber. Now, the choice of that atlas is still not unique, right? We can perform an arbitrary diffeomorphism on F, basically, and then copy over the vector space structure. So that will physically change the addition. But that's just easy to check. That's just a global isomorphism of fiber bundles. Good.
If you want to take an alternate approach, could you have said that you have a vector space structure on smooth sections?
What's that?
Could you, if you wanted to define it alternately, could you have said that you have a vector space structure on smooth sections of your bundle?
Sure. I mean, you have to do it locally because like half bundle, there's no sections at all.
But if there exists a vector space structure for the entire space of sections, then it's automatically a vector bundle.
In algebraic geometry, they define vector bundles for different things.
I think so. And that's, yeah, that's the shift up. Yeah, I'm pretty sure it's the same. But unnecessarily complicated at this point. Okay. All right. So now that we have vector bundles, we need to define bundle morphisms as usual. VB morphism. So a vector bundle morphism is a fiber-wise linear FB morphism. And that's pretty much it, right? Because now we know what it means to be linear on each fiber separately. But equivalently, you can look at it in terms of a trivialization like that. So when we talk about trivializations of vector bundles, we will always assume that they are now that they have linear transition functions, and then we can view these chi's as linear on F, linear maps from each fiber into the typical fiber, right? Because we literally induce the linear structure along these maps, so now they become linear from here to here. So we will always assume everything is linear on fibers and vector bundles, particular bundle morphisms. So in a trivialization like that, if I have a bundle morphism from E to E prime, which we call F tilde, then its local representative in two trivializations like that, alpha, the fiber part should transform by a linear map. So this thing should be a homomorphism from F to F prime, okay, i.e. a matrix. And so with this, we have the category vector bundles, categories, I guess, of all vector bundles with infinity for smooth, and vector bundles over a fixed base, where, as usual, the base morphism, this F is assumed to be identity in that category. Okay. So, example. So cylinder and Mobius are what we call line bundles. So real line bundles over the circle. And as we saw, the transition functions in these bundles can be chosen to be plus minus 1. So they are matrices of size 1 by 1 because the fiber is just a real line, and they act as multiplications by 1 and minus 1. On the cylinder, just all 1. Now, a much more interesting example, which will later turn out to be important, much later. Is the tautological bundles of Grassmannians. Okay. So let's say V is a topological vector space. What's topological vector space?
Topology is the insets, so insets are balls.
What are balls on a vector space?
Rn, so,
There's no balls on a vector space.
but there's an isomorphism to Rn, a trivial isomorphism to
I
Rn.
mean, that's unnecessary.
Just a vector space with a topology.
With what topology?
Standard topology.
Not any topology will work.
Something that
It could be not over R, right? Any topological field. What's topological field? Any algebraic structure, to make it topological, you add a topology such that the whatever algebraic operations you have are continuous in that topology, right? That's it.
Finite dimensional vector spaces is always just the standard topology in Rn.
Hmm?
Infinite dimensional vector spaces is that always just the standard topology in Rn.
You could have some other topology that would make addition and scale multiplication continuous, right?
Yeah. I mean, discrete topology also makes it continuous, right? Anyway, so topological vector space. And define its Grassmannian G sub k of V as the topological space whose points are the k-dimensional subspaces of V. Okay. So I'm not really explaining how the topology is induced on this from V, but basically you need to take k copies of V, make a direct product of them, and then you can check that the set of k-dimensional subspaces of V can be interpreted as an open subset of this with some identifications. So it's basically a topological quotient of an open subset of V times V k times. Because it's not a subset, it's a quotient of a subset. A quotient of an open subset of this. Okay. For when k equals 1, it's just literally a quotient. Because for k equals 1, it's just the set of straight lines, which is, so g1 of v will be just v, well, v minus 0 quotiented by x is equivalent to lambda x for any, scalar lambda, non-zero. What's that? Hmm? Mm-hmm. Because you need to think how to specify a subspace. The easiest way to give k linearly independent vectors that span it, right? But that's not a one-to-one thing, right? You can multiply them by any GL matrix that mixes them. They will still specify the same subspace. So that means you need to take the open subset of only linearly independent sets of k vectors, which is an open subset of this set, and then quotient that by an action of GLK.
So the GL, that K star is just GL1.
Yeah. Yeah, but it's useful to think about how it's actually constructed, but it's not very important to me right now. So I'm just saying it's topological space. You can also construct the smooth atlas on it. Let's see. Well, first of all, so G1 has a special name. Let's say if V is k to the n, where this is our field, topological field, then k t n minus 1 is defined as G1 of this V. Okay. I mean, field theory is a thing in mathematics, but not topological. So projective space. So these things are called projective spaces. They are spaces of lines. Okay, so all real and complex Grassmannians are compact smooth manifolds. Basically, because if you think about the construction of that quotient, you can figure out how to easily construct a finite atlas. What? That's useless. No. No. Okay. Yeah. Okay. So these guys are compact smooth manifolds because you can construct a finite atlas on them, where each chart consists of a pre-compact, like a ball, basically. So I'm not proving that, but it's just something I have to state. And now I'm going to define the tautological bundle. Tautological bundle, which I call, so off GK of K to the N is the rank K vector bundle, which I denote by gamma sub K comma N over GK. In which the fiber let me just write the formula. As a set, it's just the set of pairs L comma V, where L is a k-dimensional subspace. So I should just say L is an element of GK, and V is an element of L. Okay. So this is a subset of GK of the Grassmannian times right. Yeah, of that vector space, right? Yeah. Where the fiber above a point in the Grassmannian is that vector space itself. Okay, so V belongs to L. So it's pretty interesting, right? Because our base space consists, its points are vector spaces. We can define a vector bundle where the fiber above a point, which is a vector space, is that vector space itself, right? Which is why it's called tautological.
Is gamma k comma n isomorphic to V topological vector space? Because it's sort of what you're doing, right? You're quotienting out elements that are the same size.
No, it's not. I mean, its dimension is different.
like you're quotienting out points. Let's say you pick a subspace, you identify all the vectors in that subspace into one point, and then you reconstruct that vector space as a fiber over that point. And you do this for every subspace in the vector space. So you're saying the whole bundle is basically big topologically just contracted over something.
No, it's probably. I mean, it might be v minus 0, but I don't know. I don't know if that's true. No, but it could be right v minus 0, which I don't know if that's true.
Yeah, but that's also pretty
Um, I mean, for the simple examples like PR1 and RP1 and stuff, that is true. RP2, but I don't know. RP1 is a circle. A circle times a line is R2 minus 0. Right? So I don't know. Okay. There's nothing degenerate about that case.
in RP infinity, pi1 is Z2. So Z1, 2.
But you can't induce the pi1 of the whole bundle from just its base, right? Even if the fiber is contractible.
Yeah, okay.
Well, anyway. Is it clear how it's constructed? Well, how it's defined. Right. The question is, why is this really a vector bundle, for instance? But that's more of an exercise than a Blackboard story. Basically, using this representation, if you manage to construct an atlas for GK, for the Grassmannian itself, then from there, it's very easy to construct a vector bundle atlas for that. It's literally tautological, so there's. Yeah, for vector space, yeah.
So we're talking about tautological bundles. So that means that all the homotopy groups, homology groups, would be those of the base, and then the base is pretty non-trivial.
Okay.
Like it's projective space, or it's the Grassmannian, so it couldn't be v minus 0.
I guess. Okay.
Yeah, it has something to do with like how like bundles are constructed, like the topology of the bundle is.
All right. So exercise, check that these are all smooth manifolds, smooth vector bundles by constructing an atlas. It's also in the exercise book that I recommended you guys. And in particular, compute the dimension of GK of Kn. Okay. Another exercise. CP1 is the space of complex lines in C2, right? So space of C lines in C2. So as we know, CP1 is diffeomorphic to the 2 sphere because it's the Riemann sphere. Its tautological bundle is a bundle over the sphere, right? So the tautological, let me just not use that notation, but the tautological bundle of this is a complex line bundle over S2, or a real plane bundle over S2. Okay. Show that the circle bundle obtained by selecting the unit circle in each fiber is what? The half bundle.
You're saying that the associated line bundle to the line bundle is the
I mean, it means that the transition functions on the half bundle are the same as the transition functions on here, viewed as complex valued things. Okay. All right. Next definition. An object that we didn't really have for arbitrary fiber bundles is the space of sections. We have sections for fiber bundles, but they're not really a space. Right, they're not a vector space, definitely. So space of sections. So let's say E of M is a vector bundle. Have I defined sections before? For bundles, generally, probably not. So section is a map sigma from the base into E, such that pi circ sigma is identity on M. So for every point in the base, it selects one point in the fiber above that point, right? So so we can write sigma restricted to a point M will send M, will be a map from the one point set M right into the fiber above it. That's kind of a stupid way to write it. I should just say sigma of M is an element of EM, right? That's basically what this is saying. Then we define gamma of E. Sometimes people write gamma infinity, but we'll just swallow that. Is also denoted sometimes by omega 0 of M comma E. We will see that notation again at some point. Space of all sections of E. First of all, this is a vector space because we can add points in the fibers. Therefore, we can add values of sections, all right? Because the values of two different sections at the same point will belong to the same vector space, E sub M, right? So you can add them. So it's a vector space, but it's actually more. So gamma of E is a C infinity of M module, right? So C infinity of M is a ring because we can multiply functions, and it's a ring. The space of sections of a vector bundle is a ring module for that ring. Why? Because we can multiply these sections by functions on M, scalar functions on M. Specifically, if I have F, which is C infinity on M, and I have sigma, which is a section of E, then F times sigma is defined as a section, which computed at point M is of course just F of M times sigma 1. Because now this is a number. And this will turn out to be very important in the future, that it's a C infinity module, and not just a vector space.
Do you have like an example where that's useful, this observation? Like just a preview.
So you're not planning to attend. So the reason why it's important is mostly because this basically explains why you need homological algebra on the fundamental level. Like in first year linear algebra, you're studying algebra over finite dimensional vector spaces over fields, right? And that's just matrices, diagonalization, all the normal stuff, right? Here, because these algebraic structures are C infinity modules, it basically means that you will have to deal with linear algebra over a ring as opposed to a field. Because C infinity is a ring, you can divide by function. And the extension of linear algebra to rings as opposed to fields is homological algebra. For us, in terms of geometry, we will see that topological information about the base or the vector bundle will be contained in the algebraic structure of these C infinity modules, right? So for instance, we'll be able to recover at least some partial topological information about the base by studying the algebraic structures of tensor fields, like differential forms on that manifold, right? Which are sections of special vector bundles.
Well, not all expositions of like differential forms involve mention like module structures, like modules. I guess yeah.
No, but that's fundamentally right, because think of a trivial manifold M, a plane flat space, right? Then the usual argument for why you don't need homological algebra there is because you can sort of just write everything globally as a function on the vector space.
The module structure becomes kind of like a vector space. Like you can write gamma of E as like direct sums of copies of C infinity.
Right. But the way those copies are glued to each other in an algebraic sense encodes the topological information about the base or the vector bundle. Right. But even on flat space, that's a squishy argument. Like, it's not always true that you should just forget about the possible algebraic or topological non-trivialities, even on flat space, right? But anyway.
This mechanism that the algebraic structure of vector bundles on flat spaces allows you to determine that they are flat.
They give you flat modules, yeah. There's a notion of a flat module. I mean, we're not going to touch it, but it's basically, like you can think of Zn as a algebraic analog of a circle. You can take like Z, map it to Zn by taking mod n, right? You can think of that as a bundle over a circle. You can show that this bundle is not flat because there's no section in the algebraic sense. There's no homomorphism from here to here, which is a section of this projection. So this is, this type of a morphism is called not flat. But anyway, there's a lot of nomenclature in algebra, some of which very nicely matches the geometric analogy, but most of it doesn't. Okay. Anyway, let's summarize a couple more notable properties of vector bundles. Unlike general fiber bundles, vector bundles always have sections, right? Because we can construct at least one. What would that be? Okay, what is that? Right. So let's define E0 as a subset of V as the set of points that map to 0 in the typical fiber F under any trivialization. And it doesn't matter under which one because the difference is linear, so it preserves 0. Or equivalently, these points are the 0 elements of the fibers as vector spaces. What? No, we need to figure out. Right? So the projection, if I take pi and I restrict it to E0, then this will be a diffeomorphism. Because you just look at the trivialization, it's just a restriction of the trivialization maps. And once you restrict the trivializations, you just get local diffeomorphisms that match each other on the overlaps. So they glue into a global diffeomorphism. So like the existence of a bundle atlas basically ensures that this is a diffeomorphism. No, it's not a manifold atlas. It's like a, you get U alpha into U alpha. Only you get U alpha times 0 here, mapping into the U alpha by pi. But then you check that for different alphas, this is the same map. Like on U alpha beta, it turns out to be the same. By pi here, I mean pi composed with the necessary trivialization. But it turns out that the trivialization doesn't do anything to this map. So it's actually a global diffeomorphism. Yeah. I give you an example, right? The Hoff bundle, it's a good exercise. You should think about why. I give you an explicit atlas for it, right? By looking at that atlas, you should be able to figure out why there's no global section. There's no way to come up with a smooth map from the 2-sphere into the 3-sphere, which is a right inverse to the projection. That too, yeah. mean, yeah, if you're still confused, let's take the double cover. That's a bad picture. Double cover of the circle, right? The non-trivial one. And try to come up with a section for it. Well, the section for it would have to be a curve in this. But I go here, I have to lift it continuously. It has to be a smooth function. And we know that the lift is unique and it ends here. Right? So I get a discontinuous function. So there's no way to construct a continuous function from this to that. And that actually expresses the fact that the bundle is not trivial. But anyway, so this is a diffeomorphism, and obviously we can define sigma 0 as the inverse of this diffeomorphism. Okay. And this is called the zero section. Clearly, this is a section and it's smooth, so it's zero. All right. Number 2, vector bundles can be pulled back, just like fiber bundles. So let me remind you, if I have a bundle over M and I have some manifold N and I map it into the base, then I can pull back the bundle and construct a new bundle F star E over here by just copying the fiber. Well, if every fiber here is a vector space, you can copy it over and still have a vector space. So pullbacks work for vector bundles too. All right. So now I will give you a bunch of tools for constructing new vector bundles out of a given vector bundle. And basically, the idea is if I have a way to construct vector spaces out of vector spaces, then I can apply the same operation to a vector bundle fiber-wise, and I will get a new vector bundle. Okay. So for instance, I can take two vector spaces, I can tensor product them, tensor multiply, do the same to vector bundles, etc., or direct sum, or dualize, or take COM functors, or GL functors, whatever. So let's say F is it works from the category of finite dimensional vector spaces into itself, is a smooth functor by smooth I mean that it's a functor, which means that it acts not only on vector spaces but also on maps between them, matrices, right? And the space of matrices has a topology, and in that topology or smooth structure, it has to be smooth. So for instance, my map from tensor products of two vector spaces, I can tensor product matrices also, and that's a smooth operation as a function of those two matrices. I guess this could be from any number of copies of finite vector dimensional spaces too. So my definition is going to be a little bit more general than this. So a smooth functor which can act at least on isomorphisms. So some of these functors that we will use will not be defined on general MHDs. They will require invertibility of those MHDs, and then like taking the inverse. Right? So it's okay, even if it's not defined for all morphisms. Then construct it's a functor, right? It's supposed to be able to act on objects and morphisms, but not, no, at least on isomorphisms. So I want its action to be defined at least on isomorphisms.
Oh, so it might not necessarily be active.
Yeah, like one example of such a functor is inverting MHCs,
Okay.
dualizing the space and inverting MHCs correspondingly. Then that's going to be only well defined on isomorphisms, right? So then construct a new bundle out of let's say the typical fiber F is F, by replacing F by this functor of F, right? And by replacing the transition functions by this functor applied to the transition functions. Right? Because these guys are isomorphisms, and at least on isomorphisms is defined, so I can always do that. And because it's smooth, these guys will still be smooth, taking values in GL of that. So it'll be a valid smooth vector bundle. There's nothing else I need to say about this definition, and I can do examples. So these guys, they take values U alpha beta, they map it to GL of F of F. All right. So let's do example 1, dualization. I can take a vector space and replace it by its dual. This gives rise to the dualization of the vector bundle. What are the transition functions here? So here, if here the transitions are tau alpha beta, then here transitions are what? What's the adjoint? You mean transpose? What's a transpose? Okay, let's say I have a linear map between two vector spaces, V and V prime. Okay. How do I define V star? What's V star? F star, sorry. I want it to be from where to where? V star to V, V prime to V. How is it defined? So V F star of V prime is defined how? No, V prime is an arbitrary element. I'm asking.
What's the dualization factor on finite vector spaces?
I'm asking how does the dualization functor act on linear maps?
So it takes linear, basically, so like if you have some linear map f, then if you have a dual vector A acting on vector B, then A acting on FB is F star A acting on B.
Okay, so is this correct? Okay. So F star is going to be a map from what to what?
So it's going to be a map. Oh, I see. So then from because it takes in both vectors.
I think it's a map from V prime star to V star. Because then we can define it naturally. How? So remember that the star is the space of linear functionals on the vector space. So F star V prime star, so let me instead use alpha prime for an element of a dual, is supposed to be a linear functional on V, right? So I need to take this and act with it on V. So alpha prime acting on f of V, right? Okay, this defines a linear map. Right. Great. So this is how this functor works here. If I choose a basis on V and V prime, I can choose a dual basis on the stars. What is the matrix of F star going to look like?
Your organization, if you do sort of the standard thing of row vectors being your vectors and there's like column vectors being your vectors and row vectors being your dual vectors,
Mm-hmm.
row vectors, then it would be the same matrix but acting left instead of right.
Not quite, right? Because you're also trying to, at the same time, you're trying to represent it in the dual basis, right? If I transform something in V, what's the corresponding transformation in V star? Like if I rotate by 90 degrees in V, what happens to V star? It's the inverse, right? The transformation of V star is always opposite, inverse to V. Why is that? Because, yeah, but so just looking at the formula, let's say I have alpha and F times V, right? Let's say F for now is from V to V itself, okay? Then I can write something like that. This is supposed to be equal to F star alpha comma V. By comma, I mean the pairing, the usual pairing. No. I'm using just the pairing between dual V star and V. Yeah. Then the let's write this out maybe. How do I write in the basis? So I need to pick EI, basis EI, and the dual basis will be alpha j. And Fij is going to be what? The matrix element ij. How are we going to define it? So alpha j, okay. Let's just use covariant notation right away. Okay. Right. because when I act on the basis vector, I get the ith column of f, and this extracts the jth element of the ith column. So that's Fij. Okay. Now let's write out the other thing. So f star I ij. What is that? I need to do the same only on the dual space, right? So this is supposed to be vi comma f star alpha j. EI, sorry. But this is equal to f ei alpha j. Equal to what?
Alpha j f it's a number, right? Doesn't matter if the dual vector is acting on a vector or if the vector is acting on a dual vector.
Yeah, there's this double dual thing, which is not pleasant. Wait, how does it work? It's supposed to be equal to that. Let's call v fv v tilde or something. Then v will be equal to f inverse v tilde. Okay, so this equals f star alpha v, oops. And this equals just alpha v tilde. And this equals f star f inverse star. That doesn't prove anything.
Maybe just avoid using the parrots and just say we're expanding the action of that basis vector. Like if you want to write the transitions in terms of tau alpha beta, they're literally just going to be tau star. Why are we even going through the basis?
I forgot the good argument. It's supposed to be tau alpha beta star inverse. Okay.
Oh, of course, right? Because if tau alpha beta is a transition between like the fiber, let's say it's a transition between the fiber over a point in the alpha description to a fiber over the point in the beta description. Call it f alpha and f beta. Wait.
Now I know that intuition, that doesn't prove anything.
Right.
Basically, that makes this functor covariant as opposed to contravariant. But I think maybe I should think about it again. But at this point, let's just say it's a definition.
Can you also say that the double
It's identity anyway, right? But let's just say it's a definition because we want a covariant functor. Okay.
That is yeah. Right. So if you have a dual of the line bundle, the transition functions are 1 over x as opposed to x. Like if x is the GL1 scaling transformation, the transition functions are smaller. It's important.
that's like the covariant transformation law, right? If your basis, if the matrix that transforms your basis is like C, then the matrix that transforms coordinates of vectors will be C transpose inverse. Same idea. Yeah. No. Star is the dualization that we just discussed. You can think of it as transpose.
This tau acts on the vector space.
So you want transition functions on the dual space, not on the vector space. And the dual space is a different vector space, even though maybe is morphic to the original vector space. So tau is a function that acts on F, not on F star. You need to construct a function that acts on F star from tau, and that is tau star.
Or if we have linear transformation of vector space, it can't act on dual vectors. That's not defined. But there's a natural way to define such an object corresponding to
Basically, I think this argument might work. So let's say we have E and E star. I want to be able to have a natural pairing between these guys that is globally defined, so it shouldn't be independent of my taus, right? So I have E and E star, let's say, 2 points which are in the 2 fibers above the same base point, right? So I should be able to pair them. And now let's go to a different chart. Go to a different let's call them, so these, let's say this is an F, this is an F star, right? And they are above some point M. Then if I go to the next chart, then these will transform by tau alpha beta E, and this will transform to tau alpha beta star inverse E prime, right? And now by definition of star, this is tau alpha beta inverse tau alpha beta E star, and this is 1, which is good. So this pairing is actually globally defined. So that's probably the easiest way to explain why it's defined that way.
It's the pairing that has to be fixed.
Yeah.
Changing trivialization.
All right. Yeah. Okay. Yeah.
You can define duals on the same thing you want.
Yeah, dude, pointwise dual.
Or if we define the dual globally on the infinity module, we get the same thing, right?
Then you get the space of section. The space of section.
Yes.
Section. Okay. You need to define one.
And he's trying to define the bundles in the sheaf sense. Sure, you can do it. All right. Not here. Not unless you want to replace eventually your fields with something else, rings and stuff. Okay. More examples. We have E direct sum of E prime. Transitions are, of course, tau plus tau prime. We know what direct sum of matrices is. Just block diagonal matrices. This is E. Okay. Then E tensor, E prime, of course, will be tensor product of transitions. All right. Next definition, subbundle. So let's say E is a bundle. If E prime is a subset of E, such that pi restricted to E prime is a smooth VB, then E prime is a subbundle of E. So basically, a subbundle is just smoothly choosing a subspace of the fiber above every point of M. Yes.
Your fiber over each point has to be a vector space. And the only vector spaces, the only subsets of vector space that can share the same projector have to be subspaces in the vector space.
One more thing that's unique, special to vector bundles is frames. Let's define a local frame on E of rank, if the bundle is of rank K, is an open set. Well, it is defined on an open set U and M, and a collection of local sections by local sections EI. So each of these maps from U back into E, restricted to U, such that for every M in U, the set of these vectors evaluated at M is linearly independent. Okay, that's a frame. The frame is global if U is all of M. And we also define N frames. An N frame is just a set of N linearly independent local sections. So N linearly independent local sections. By the way, being linearly independent at every point is the same as being C infinity module linearly independent overall, if you like that more. Yeah. Yeah. Okay. Proposition. If we have two vector bundles over the same base, then the space of sections of E tensor E prime is naturally isomorphic to the tensor product over C infinity, so tensor product of modules gamma of E prime. Okay. And I'm too lazy to prove it. But I'll give you the idea. Right, so what this is saying is that if I have a sigma, which is a section of this tensor product, then sigma can be written as a sum of some function times a tensor product. So I don't know what to call. Let's call this S. And then sigma I tensor sigma. Let's call them J prime LM. Okay, with some IJ, whatever, right?
Do they have to be Manet sums, or can they be constant?
That's the thing, because this is an arbitrary function, you can cut off with that. Right?
Oh, I see.
They don't even have to be frames, so you can just banish them outside of a local thing. So that's exactly what the C infinity does, right? It allows you to not worry about global properties. Okay. I mean, the idea is, let's take E and E prime to be both trivial. If they're both trivial, then we can represent all sections globally as F valued maps or F prime valued maps, and then you just take this and you show that it's an isomorphism. That this operation, tensor producting two sections, is an isomorphism of vector spaces between these two things. Trivially, because there's just F tensor F prime. You can always go back. And then there's a theorem which we'll prove later, that every vector bundle is a direct summoned in a trivial bundle. So like for every E, there exists an E tilde such that E direct sum E tilde is trivial. And then you can just deduce the rest of the theorem from the proof for trivial bundles. There's a more direct way which doesn't involve this theorem, but in the process you will essentially prove that theorem at the same time. So it's just counterproductive. But you can use some partition of unity to glue the different local frames, and, but it's messy. Okay, it's just something that we will use when talking about tensors. Distribution. A distribution is a choice of linear subspace dm and em for each m. No restrictions on smoothness. So not necessarily a subbundle. Moreover, the dimension of that subspace can jump from one point to another. So no restrictions on continuity of dimension, etc. But if the dimension is constant, then we say that it's a distribution of rank, whatever the dimension. Okay, so theorem number one, a vector bundle is trivial if it has a global frame. Why? Huh? Yeah. Trivial means a direct product. A bundle atlas consisting of one chart. So you can construct a chi from E into M times F, defined as chi of E is chi of E over point M is M comma
Take the components of each phrase,
yeah,
basis of that.
yeah. I'm too lazy. E I. Now I'm got myself into a corner. Of I. So this is a basis of F. These are components in the global frame. Now that's bad. Let's call this V. VI. So this V is equal to sum of VI, EI of M. Okay. Take these numbers, plug into there, you get an isomorphism, which is a global trivialization for you. Okay. So like on flat space, I can pick my constant basis vector fields, right, and expand everything in them. And obviously the bundle is trivial because we can write everything in terms of x hat, y hat, z hat. We don't need to worry about choice of frame. Number two, a distribution D is a subbundle if and only if it has local frames. Okay, i.e. collections of locally linearly independent maps that take values in D and are smooth sections of the whole bundle and span D pointwise. Number three, subbundles are embedded submanifolds. Embedded manifolds. Number four, go here. This is actually a pretty useful one for constructing even more bundles. For every BB morphism F from E to E prime of constant rank on fibers, right? It's a linear map on every fiber, so rank is a well-defined notion. The distributions kernel F, which is defined as the disjoint union over LM of the kernels of the fiber-wise maps, and also image. So this is a subset of E, and image F is going to be disjoint union. Let's call this image FM. This is a subset of E prime. Are subbundles. That's pretty powerful because, for instance, you can define antisymmetric tensors as tensors that vanish under the symmetrization map. And immediately you know that that's a subbundle. Right? You don't need to construct any atlases or anything. And finally, number 5, if E prime is a subbundle, then E over E prime is also a vector bundle, where this is just defined as the disjoint union, of the factors of vector spaces. But then the transition functions can also be factorized because of linearity. Quotient of vector spaces. It's like a quotient by a subgroup, abelian subgroup.
Equate two vectors if they differ by an element.
Yeah. Okay, so I'm not really going to prove these, but the statement about frames should be more or less clear about distributions, that they are subbundles if and only if they have local frames, because local frames is exactly what lets you construct local trivializations, just like in the first one. And then these guys, you can show that they are subbundles by just constructing frames for them. For any map, you just think, how do I construct a frame for this subbundle? Based on the fact that F has constant rank, that's more or less obviously always possible, yeah. And last one is something we've already stated before, but basically, you remember the statement from fiber bundles that if I have a cocycle of transition functions in my typical fiber, that lets me reconstruct the bundle as a disjoint union of these, and then factored by the action of transition functions on the second component, right? So exactly the same thing holds for vector bundles, of course. So you can, by having a cocycle that consists of linear GL valued taus, you can reconstruct the vector bundle up to an isomorphism. But that's all we care about anyway. Okay. What time is it? 3:45. Oh, okay. So we are ready to define the tangent bundle. What? Hello. So tangent bundle, we know what tangent vectors are. We don't know that they constitute a vector bundle because we need to construct an atlas for it. So definition, M is a manifold. U alpha comma phi alpha is a smooth atlas for M. Then Tm will be defined as the disjoint union of the tangent spaces that we've defined before, which we already know are vector spaces, with the structure of a vector bundle specified by the vector bundle atlas what would this atlas consist of? So we need to take Tm restricted to U alpha and map it into U alpha. Let's say it's dimension n. Okay, map it to U alpha cross Rn.
So we already have we have equals basis from our manifold.
Mm -hmm.
So we can essentially use a projection of that basis or a representation of that basis with our
Right. Mm-hmm. So we have our phi alpha, which acts on U alpha and gives you and goes to Rn, right? So we can take its differential, and it's going to be a map from right at a, let's say at a fixed point. It's going to be from Tm U alpha, which is the same as TMM, to Rn cross Rn, right? So what should I make my? So it's actually, sorry, now it's just a vector space. So it's in T at phi alpha of m over n, which is itself Rn, right? Okay. So here we have maps that take the tangent space, which is, I can write m here safely, spits out a vector in Rn. So I can just make these my trivializations. So chi alpha of a vector is going to be defined as the projection of that vector, comma, this thing. Let's call this M, V. Right. And this thing belongs to Rn. So a pretty tautological construction, right? The Jacobian matrices of these chart maps literally give us the bundle atlas. I mean, we don't need those now, but yeah, the transition functions are going to be differentials of the transition functions. Cool. So explicitly, what does this mean? It means that explicitly m comma v, an element of the tangent bundle, so a tangent vector above a point m, is represented as x1, etc., xn. Right, that's the coordinates for m. And then comma vi di, where di is a special frame. Where di di is the sum of vi d by dxi, where this is just a notation for the standard basis on Rn. Okay. Yeah, differential. So this is so the frame on the manifold itself, di, is denoted. This is actually phi alpha star inverse of d by dxi. Right. So if I think of my standard basis on Rn, I can pull it back by this differential and get a vector on my manifold, a tangent vector, right? And that's going to be a local section of the tangent bundle because everything here is smooth, so it's a smooth map into the tangent bundle. That's just a notation for it. Okay. So we will usually write tangent vectors or vector fields in terms of these local frames if we use coordinates. Let's define vector fields. Vector fields are sections of Tm. We denote the space of vector fields by this script x. The space of sections of Tm. Locally, any vector space x restricted to some sufficiently small chart is just written as xi times, well, even more generally, yeah, we can write ei, where this is any local frame for Tm. And these guys are C infinity on U. So they're decomposed in terms of any frame with functional coefficients. Again, C infinity modulo. And there's a, so let me, maybe my last comment. There's an interesting notion of actually one of the possible approaches to connections in like classical general relativity. And if you read books about like Cartan geometry and all that, people often talk about parallelism. Parallelism is like a very simple way to introduce a connection on some special manifolds. So first of all, a manifold is called parallelizable if Tm is trivial, i.e. there is a global frame of tangent vectors and vector fields. A specific choice of a global frame is called parallelism. And it defines a flat connection. So it defines a flat connection where during parallel transport, the components of a vector in the global frame remain constant. You just parallel transport it without changing its components with the chosen frame.
So basically, just helps to compare vectors at two different points and stay safe parallel to each other.
Right. So like on the plane, for instance, I can choose Cartesian coordinates and parallel if I have a tangent vector here that looks to the right, and then parallel transport along any curve, it'll still look to the right. But I can take polar coordinates, right, in the plane minus a point, and then if I take a vector that looks in this direction here and I parallel transport it somewhere, it'll look in that direction now. So it's a different parallel transport. You know. What? No, it's not a different manifold. But I can take out a point here too.
So, so if we have a flat connection, we need only specify the entire connection. We can only specify attachment basis vectors, and that gives us this frame.
Say it again.
Or if we have a flat connection, if we want a complete description of some flat connection, we can just choose a frame at a point, and then that generates.
No, the global frame gives you a complete description of a flat connection because it does. The global frame tells you that if you have a vector, the global frame A allows you to write any vector at any point in a particular basis. So it tells you that if you want to transport this vector to somewhere else, just transport its components in that global frame. In that basis.
If we go the other way though, and we have a flat connection, we can say that it's equivalent to the parallelism, and that we just choose a frame at a point, and from that determine their frame.
Right. So the notion of parallelizability is pretty interesting because for a long time, it was not even known which of the spheres are parallelizable. So I'll just tell you a little bit about the resolution of that question. So the spheres Sn, so which spheres are parallelizable? Right. So we know that S0 is parallelizable is just 2 points. S1 is a circle, so it's also parallelizable. There's a global frame that consists of this vector field that rotates. So parallelizable. S2, why is that not parallelizable? So what does that say?
So your frame bundle will be essentially a collection of two vector fields, which are linearly independent everywhere, but they can except at two points. Except that means they can't vanish anywhere.
Yeah. Elements of a global frame cannot vanish anywhere, but we know that on a sphere that's not possible. Do you know a simple proof, by the way, of that? Yeah.
You do this thing with homotopic where you rotate. There are easier ones.
Reball theorem. It's equivalent to some fixed point theorem. It's equivalent to the statement that every diffeomorphism of the two-sphere orientation preserving one has to have a fixed point. Basically, you take whatever vector field you picked and you look at its flow under, some infinitesimal amount of time. Its flow under an infinitesimal amount of time. That has to be an orientation preserving diffeomorphism of S2, but that has to have a fixed point. And basically, by sending time to 0 and taking a derivative, you can figure out that it produces a 0 of the vector field. What? Why? Yeah. Yeah, sure. S3. Turns out it is parallelizable. You can construct three linearly independent vector fields on it. But the easiest way is by realizing that this is SU2, and every Lie group is parallelizable because it has the, let's say, left invariant vector fields, which are not zero anywhere. The tangent bundle of any Lie group is isomorphic to that Lie group times the Lie algebra at the identity. So. S4, no. S5, no. S6, no. 7?
Yes.
Yes. Right. S7 also. But S7 is not a Lie group, so that's kind of weird. But it's actually the unit sphere in the space of octonions.
Right. S3 is a unit sphere.
Unit sphere in quaternions. Unit sphere in unit sphere in complex numbers, unit sphere in real numbers. Okay, so those, if you use that analogy, then it's sort of intuitive why this would be also, because you can still use octonions to construct linearly independent vector fields, even if it's not a Lie algebra. But the question is, are there any more parallelizable spheres? And that question is the difficult one. And so answering to that question was basically the first big success of K-theory, which is the theory of some classificational theory. I don't know. So it's the it's called the Horowitz Radon-Ekman theorem, and it says the following. Let's say n is the dimension of my sphere, natural number. Write n uniquely in the form k times 2 to the nu, where this is odd. Okay, this is unique. Then write nu in the form 4b plus c, where c is between 0 and 3. And then define rho of n as 8b plus 2 to the c. Notice that it's independent of k, actually. Then Sn has Sn minus 1 has rho of n minus 1 linearly independent vector fields and no more. Right, so this is the largest global K-frame that you can construct. And if you write out the table of what these numbers look like, it's going to be 2 to the nu here and rho of n here. So 1, 2, 4, 8, 16. Goes 1, 2, 4, 8, 9, 10, and then 12, then 16. Whereas this is 32, 64, 128, right? So these will be parallelizable because the number of vector fields will match the dimension. But there it starts to diverge. There's too few vector fields to give you a global frame. The proof is, the easy part is to construct these vector fields, and that uses Clifford algebra spinners and Clifford algebras to construct them. But the difficult part is proving that there's no more, and that's K-theory. So I thought it's kind of a fun.
Associativity, what else would you give up then?
Nothing. Mm-hmm. I mean, that might be an intuitive explanation for you, but it's not the proof of anything. Right? No, but right, how is parallelizability related to an existence of an algebraic structure? It's not, right?